So the first chapter, which in physics this year, 10th, is force. We also had force last year, but this year we are not looking into the not looking much into the translational effect of force. Rather, we are interested in the turning effect of force. So as we know that forces can be used to translate object. Translate means move it in one direction. But the same forces can also be used to rotate object. Okay, sometime when like if you strike a object at certain angle, they start rotating rather than translating. Common life experiences could be when you are pedaling a cycle. The wheel rotates. The cycle do go forward, but wheel also rotates. Okay, those hand fans, we apply force in such a way that it oscillates, like more like a half circle kind of rotation. So such effect of force is what we are going to see in this chapter. So briefing, what are the different effects of force? Force can change the state of body, or it can change the shape and size of the body. Basically means it can deform a body. If a body is like a car is in rest, force applied on the car can change the state of rest. Like if we want to move the car, we generally apply acceleration force on the car and the car starts moving. So this way, by applying force on the car, we are changing its state of rest. Similarly, if a car is already moving, we can apply a backward force in form of brakes, and brakes will bring car to a rest. The second thing which force does on a body, it deforms the body. It can change the shape and size of the body. Like for example, if you have a tin cane and you try to press the can, the can gets compressed, means there is a deformation. Similarly, if there is a rod and like you try to bend it, okay, by applying force, so the rod will bend. Again, there is a deformation. So force generally produces two effects on body. It can either change the state of rest of the body, change the state of the body, which means the state of rest or motion, or it can change the shape and the size of the body. Generally, we have two kinds of motion, though we have other types of motion also. First is translational motion. Second is rotational motion. These are the two motions about which we are going to study. In fact, the translation motion, as I said, you have also studied about it in ninth standard. So, what is translation motion? If a force is applied on a rigid body and the body starts to move in a straight path in the direction of motion, it is called as translational motion. Last year, if you remember, the chapter name was motion in a straight line, right? Because those body were actually translating. They were just going in the straight line. Means if you push an object by applying force, body moves in the direction of force applied. Okay. So these kind of motions are called as translation motion. In this type of motion, the entire body covers the same distance in the same time. For example, again, this body itself, okay, maybe this is the front section of the, like, this is the front portion of the car, and this is the back portion of the car. When the body is translating and moving forward, okay, probably this point comes here. Okay, I'll just draw the car again. And this point B comes here. So every part of the body moves together. That is what translation means. So there is no relative motion between the object. It's not that one part of the body traveled less and the other part of the body traveled more. So every single part of the body travels the same distance in translational motion. Clear?
Can it happen? I mean, can you give an example where the body does not move in the same distance at the same time? The
The
only translation, right?
like different part of the body doesn't travel same distance. You mean like that? Yeah,
Yes.
that will be seen in the next type of motion, which is
Okay.
rotational motion.
Okay.
So that's there. Okay. So next, if a body is pivoted at a point and a force is applied on a suitable point, it rotates about the axis, passing through the pivoted point. This kind of motion is called as rotatory motion. Okay. Now imagine like a body here, which is rotating about a fixed axis. Like this point is pivoted and it's moving around. It's rotating like this. Now imagine 2 points on this circle during the rotational motion, point A and point B. Okay, during one circle, A covers this much distance, while during the same circle, this covers this much distance. So are the 2 points A and B covering the same distance in the given time or different distance?
Different.
So they are covering different distance in the same amount of time. That is why this is rotational motion. So in rotational motion, different part of body may cover different distances in the same amount of time. Okay, so that's the point too. In this type of motion, different part of body covers same difference. Oh, okay. Wait. There's some mistake. It has to be different. Different distance in the same time. Okay. Apart from this, there are other motions also which you will study in higher classes. Something like simple harmonic motion, where body is oscillating forward and backward, like normal oscillatory motions. In oscillatory motion, body doesn't complete a full circle. It goes forward, backward, right? Something like a motion of a pendulum. We studied last year a bit about it. So there can be other kind of motions also. All right, but briefly this year now we are focusing in this chapter we are going to focus more on the rotatory motion because we have idea about translational motion from last year. Okay, with respect to rotational motion, a physical quantity is very important, which is known as moment of force, also known as torque, which also means the turning effect of force. Okay, so force, whenever we need to turn an object, like suppose this is a stick which is hinged at this point, and I want to rotate it like this. For rotating an object about a fixed point, we need a force, correct? Same even is required for translation. For moving an object in a straight line, there also we needed a force. But in this case, like in translational motion, we were sure that if we apply more force, there will be greater translation. The body might move greater distance in lesser time, correct? But same logic is not applicable here. In rotational motion, sometime by applying more force, we are still able to rotate less. So force, though, is like responsible for rotating an object, but it is not directly responsible for how much of rotation because there are other factors which also come into play. So if you want to really understand what is the effect of rotation, like how much rotation it can a force can apply, force sufficient is not sufficient to explain that completely. We need to see what is moment of that force. Okay, so what I mean to say is, if suppose there is an object on which we are applying force, let's say the same some force 5 Newton. Just tell me logically, oh, where the turning effect is more, if I apply 5 Newton here or if I apply the same 5 Newton here. This is a fixed point, like this point A and point B. So we are applying 5 Newton force either at A or at B. In which of the two cases the turning effect would be greater? It would be more easy or the rod can rotate greater to a greater extent
In B. In B.
in B.
Yeah.
Okay, that's a common observation, right? So if we apply the same force from a greater distance from the pivoted point, the turning effect would be greater. It can produce greater turning effect. So that is what moment of force means. How much turning effect is being produced by a force, which not only depends on the force, but also depends on how far the force is being applied. Correct? So force is not only like not just force is sufficient to explain the turning effect. Pivoted means basically being fixed at a point. So when you fix an object about a given point, then that point is called as the pivoted point. Like if suppose, see, whenever you want to rotate an object, you need to technically pivot it around a point. Okay. So like suppose this is a rod. If I fix it here, if I nail it here, so that it can turn around the nail, it's not that it is completely fixed, then that becomes the fixed point is the pivoted point.
Okay.
So moment of force is represented by symbol tau, and it is product of the force applied and the perpendicular distance of force applied from the pivoted point. So greater the distance, greater the force. So basically, this is dependent on two factors. One is how much force you are applying. Second is how far you are applying. So you can increase moment of force even by like for the same force can have different moments given that it is at different distance from the fixed point. Torque. So torque depends on two factors as we said. It depends on force, the force applied on the body, and it also depends on the perpendicular distance of the force applied from the pivoted point. Therefore, therefore the formula for torque is torque or turning effect is same. So therefore formula for torque is force multiplied with the perpendicular distance. Okay. Now, why they're calling perpendicular distance? What does that mean? Like for example, if this is some object, let's say, and here we have a force, like force is acting on this object like this, in this direction. Okay. Or maybe like here at this point. This is the pivoted point, and this is the point, like force is applied on point A. Then what is distance of the pivoted point from the force? We don't take this distance, is what I want you to understand. Don't take the distance of the point where the force is being applied from the pivoted point. Take the perpendicular distance of the force being applied. Okay, how do we take the perpendicular distance? Extend this force in the same direction and take the shortest distance of the force vector from the pivoted point, means the perpendicular distance. Okay, so whichever direction force is acting, you extend that force and try to take the shortest distance of that force direction from the pivoted point. Okay, not this point. Am I clear? See, when in mostly while doing numericals, what happens is we have rod like this, and here we have a pivoted point. Force is acting like this. So in this case, the point where force is acting, like A, okay, distance of that from the pivoted point and the perpendicular distance both are same. So we don't have much confusion. But see, though this situation won't come, okay. But suppose force is acting like this. Just imagine, just hypothetically, that imagine that force is acting like this. Then in that case, this is not the shortest distance of force from the pivoted point. Okay, in this case, we need to extend the force arrow forward. Am I clear? Okay. This understanding would be required more in higher classes because here they won't give you, like for rods, they won't give you this question, but they may give you questions like this, small application based questions like this. One of them is there in the exercise itself. We'll see that later. So force is okay. So these are the two factors. If they ask you what are the factors affecting torque, you just need to write this: force applied on the body and the perpendicular distance of force applied from the pivoted point. Okay. Okay. Therefore, going back, since a torque is equals to force multiplied with distance, and unit for SI unit for force is Newton, while distance is meter, SI unit for torque is Newton multiplied with meter. Whereas CGS unit for force is is dyne, and for distance is centimeter. So torque would be dyne centimeter. So these are SI units for torque and CGS unit for torque. Also in exam they ask you what is relation between SI unit and CGS unit. Means what is relation between Newton meter and dyne centimeter. We have learned this earlier that 1 Newton is equals to 10 to the power 5 dyne, right? If you forgot that, that can also be derived. That's not so difficult. But for the timing, let's just learn this. 1 Newton is 10 to the power 5 dyne, and 1 meter is 100 centimeter, or 10 to the power 2 centimeter. Okay, multiplying all the 10 terms, this is 10 to the power 7 is 10 to the power 7 dyne centimeter. So 1 Newton meter is 10 to the power 7 dyne centimeter. That is your relation between Newton meter and dyne centimeter. Okay, we need to remember this can come directly for one marker. Here, next, what are the different types of moment? Moments can produce two kind of effect on a body. Means it can either rotate body clockwise or it can rotate anti-clockwise. Though that also depends on the observer. Because if suppose if I'm rotating an object in a clockwise direction with respect to my observer, maybe for a person who is standing on the other side of the object might feel that the object is rotating in anti-clockwise direction. Correct? That also depends on the observer. But okay, let's say with respect to one observer, when a force acting on a body is applied to a body pivoted at a point, and if the body moves in the direction of motion of hands of a clock, means the way the hands of a clock moves, it produces a clockwise movement, stating that body is moving in clockwise direction with respect to the observer. Suppose we have an object like this pivoted at this point. Okay, I apply a force like this, 5 Newton. Just think logically and tell me what do you think will be the nature of the moment with respect to our observation, like from the direction we are looking at the screen. Will it produce a clockwise movement or anti-clockwise movement?
Clockwise.
Clockwise.
This is clockwise movement. Okay, let me change the let's change the force. The same 5 Newton now acting here in the same direction. Okay, let me not change the direction also. Like this is towards right, and this is also towards right. So 5 Newton here, you said clockwise. Okay, remove that force. This force is also acting towards the right direction itself. What do you think? What would be nature of due to this force? Clockwise or anti-clockwise?
Anti.
Anti-clockwise.
So though the force direction has not changed, the nature of moment, the direction of moment has changed. Correct? Okay, let's try to add force from the other side. Okay, this is 5 Newton. Now towards the left direction, clockwise or anti-clockwise?
Anti-clockwise.
Clockwise.
Anti-clockwise. And 5 Newton here,
Clockwise.
Clockwise.
that clockwise. Okay. So let's see quickly for with respect to a rod. 5 Newton here,
Clockwise.
clockwise. 5 Newton here,
Anti-clockwise.
anti-clockwise. 5 Newton here,
Clockwise.
Clockwise.
5 Newton here.
Anti-clockwise.
Okay. This understanding will be very useful in solving some simple numericals. Okay. If you understood this, mostly students struggle with this part sometime. So when we come to that, we to those numericals, we'll see the application there. So let's go ahead with the definition now. When a force is applied to a body pivoted at a point, and if the body moves in the direction of the motion of hands of a clock, it produces clockwise movement. Means we are familiar how the clock hands move. Okay. And similarly, anti-clockwise movement means when the force applied on the same body tends to move the body in the direction opposite to the direction of motion of hands of the clock. Okay, so when a force is applied to a body pivoted at a point, and if the body moves in anti-clockwise direction, like opposite to the direction of motion of the hands of the clock, then the moment produced is anti-clockwise moment. A certain application for what we have seen, the moment of torque. Why handles are fixed at the free end of the door? Like, if,
Thing.
yeah, sorry.
The handle is kept like far away from the pivoted point so that it
Yes.
would be easy to open it without like
Less
more of
force is
force.
needed to. Yeah.
Yeah, with less force you can open the door.
Okay. So we can, for explanation, we can say since turning effect is force into displacement, we can like if the handles are kept far away from the door. Okay, if that means the distance is more. This is just our understanding. The distance is more, so we can get greater turning effect even for a lesser force applied. So to achieve greater turning effect by applying lesser effort. Am I clear? Even we see other applications of this turning effect. One is what is this?
That's a mixer, like a.
Grinder type.
Yeah.
It's it's a this is used for grinding flours, like grinding rice and producing flour from it. So the upper circular stone of a hand floor grinder has a handle near to its rim. Okay, so we can see clearly in the picture that this is like the pivoted point or the axis of rotation, and the handle is a bit far away from the axis. Okay, so even here we can say the same thing. This is to achieve more turning effect or torque by applying lesser effort. We do see more applications of such in our day-to-day life. So first, here you see the pedal of a cycle. Even in the pedal of a cycle, you see that the pedals are generally a bit far away from the axis of rotation or the fixed point. This is again to achieve the same greater turning effect. And this here is a spanner which is used to untie the knot. Okay, so if you have ever used it or have seen people using it, you know the hand is like the effort is applied as far away from the turning point because this is the pivoted point for turning, right? And we try to apply the force or the effort at maximum distance from that pivoted point. So these are some common examples of turning effect in daily life and how we can increase the turning effect by increasing the distance where we are applying the force from the pivoted point. Okay. Next, a scenario where two forces acts on a body pivoted at a point. So let's take a body. Let's say okay.
Yes, sir.
Okay. So here two forces acts on a body which is pivoted at a point, and let's take some value here. Let's say this is 5 meter and this is also 5 meter. Force F1 is 5 Newton and force F2 is also 5 Newton. So here we have two forces. So see in many time now in real life situation you will come across situation where there are more than one force acting on a given body, and each of these forces will have some turning effect, can have some of their own turning effects. So let's see what is the combined effect of turning what is the combined effect of individual turning effect in this case. Okay, so let's go one by one. What is torque due to force 1? Let's call that as tau 1. By formula this is 5 newton multiplied with 5 meter, so 25 newton meter. I think that's not sufficient, right? We need to add direction to it. So can you tell what is the direction of this turning effect? Is it
Clockwise.
Clockwise.
clockwise? Okay, similarly, tau 2, turning effect due to force 2, is 5 Newton multiplied with 5 meter again. So now here it's again 25 Newton meter, but then what is the turning effect there?
Anti-clockwise.
Anti-clockwise. Okay, so chalo, if suppose we conventionally give a sign to this clockwise and anti-clockwise moment, let's take one as positive and the other one as negative. What is net turning effect due to the two force?
Zero.
Zero.
Zero. Okay, so just 0 Newton meter. So whenever there are more than one turning effect on a body due to two different forces or more than two different forces, the combined effect, when we are finding that combined effect, we in that case we have to see like how much clockwise turning effect is there and how much anti-clockwise turning effect is there. If suppose the two turning effects are equal in magnitude, they certainly have a opposite direction. Sometimes teachers do give a direction like minus and plus to that. I think that's not really important from ICSE point of view for you to know which one is positive, which one is negative. Because in the textbook, they have never specified, nor in the syllabus, there's a mention that we should know which one is positive and which one is negative. All right. Suppose there are two torques, like for example, T1 and T2. This is 30 clockwise and this is 25 anti-clockwise. Can you tell me what is resultant torque because of these two torques? One is 25 anti-clockwise and the other is 30 clockwise. So what is resultant of these two?
-5.
Okay, so as I said, no, we don't worry much about the minus or the plus
Okay.
sign
Okay.
here.
Yeah.
So it is 5, the resultant is 5. Now this 5 is in which direction?
Clockwise.
Clockwise.
Clockwise. You understand this? Because clockwise was more, right? So 25 anti-clockwise cancel 25 clockwise and there is 5 extra in the clockwise direction. Clear?
Cancel each other as much as possible, and what is left out is.
Yeah, that much in the other direction. In the direction in which the value is more. Like for example, if I have 30 clockwise and 25, 30 anti-clockwise and 25 clockwise, then what is the resultant?
5 anti-clockwise.
Anti-clockwise. Yeah, that's all. Okay, so some questions they will ask you to find the resultant of two torque. So you just see which one is greater and the extra you take in that direction. Clear? Okay. Next, again, a very important definition is here. Couple. They do ask you what is couple? What is its understanding and formula? So in case of couple, this is a special case where two forces are there acting on a body and are producing their own moments, all right, or their own turning effect. But this is a special case where two equal and opposite parallel forces not acting along the same line forms a couple. So in this case, one force is acting like this and one force is acting like this. They're equal, therefore I've written both of them as F. Okay, let's say distance of this one is D from the pivoted point, and this is also D. The total distance between the two forces is, let's say, okay, this is D1 and D2, and the total force distance is D. So it is not compulsory that the distance is same, like it can be D1 and D2 distance from the pivoted point. Only thing which is necessary is that they're not acting in the same direction. Okay, so they're one is acting down, one is acting up. So in this case, okay, if I observe here, what is the distance between, or what is the turning effect due to this first force F1 or F, this red force? How much is turning effect due to the red force? In terms of, you don't know the value, so in terms of the variable, can you tell? Like, what's the turning effect due to the red force?
F into T1.
Into D1.
F into D1. Clockwise or anti-clockwise? Anti-clockwise. Okay. And what is turning effect due to the other force F?
F into D2.
Okay. And this is?
That's
Clockwise.
clockwise.
Are you sure?
Yes, sir.
Think again.
No, it's anti-clockwise.
Anti-clockwise.
Goes like
This is again anti-clockwise. Okay. This force is trying to turn it like this, and this force is also trying to turn it like this. So both forces have anti-clockwise turning effect. Therefore, total turning effect is nothing but F times D1 plus D2. Okay. Uh, which is nothing but F into the total distance D. So the net combined turning effect due to two opposite forces which are not acting along the same line is called as couple, or they form a couple when two forces don't act along the same line. Force times the distance between the two forces. This, like if they ask you define couple, so you can say when two equal and opposite parallel forces which are not acting along the same line, they form a couple. Okay, two opposite and parallel forces which are not acting along the same line forms a couple. Then if they say derive the formula for moment of a couple, then we do this. Draw a rod, apply two forces F and F on at distance D1 and D2, so that the distance between them is D. Okay. Uh, Find the individual turning effect FD1, FD2, add them, you get F into D because D is D1 plus D2. So the turning effect due to couple is force into the distance between the two forces. Okay, this theoretically, derivation and the formula. I hope that's fine for a couple. See here, I would like to just add one point which is not given there in the textbook. It is again not compulsory that the forces are on either side of the pivot. It can also be possible that the forces are on the same side of the pivot. Okay. Another situation where there are two forces acting on the, like two equal forces are acting, but this time the two forces are on the same side of the pivot, F and F. Distance of force from the pivot is D1, and distance of the other force from the pivot is D2. Okay, let's try to calculate total turning effect because of the two forces. Turning effect due to force, the first force is F into D1. Okay, this is clockwise or anti-clockwise?
clockwise.
Clockwise. Okay, and the other is FD2. This is anti-clockwise. In this case, the two torques or the two turning effects are have opposite direction. Okay, just by your general observation, can you tell me which one is greater? What, which one do you think is greater?
F into D2.
Anti-clock.
F into D2, because both forces are same, so I think it's directly proportional to the distance. So D2 is more than D1, and therefore I can say that the net turning effect would be F D2 minus D1 anti-clockwise direction, isn't it?
Yes.
FD2 minus FD1 in the anti-clockwise direction. Okay, this D is again distance between the two forces. Okay, the perpendicular distance between the two forces D. Okay, what is magnitude of this D in terms of the two distances? Can I not say this is D2 minus D1? Force, the top
Yes.
force is D1, the bottom force is D2. So how much is this distance between the two forces?
D2 minus D.
D2 minus D1. So even here we can say torque is F into D. Understood? So all we need to understand in this couple part is if there are two forces acting on a body, two equal forces acting on a body in opposite direction, then the total turning effect due to two force is equals to product of individual force times the perpendicular distance between the two force and multiply it with the distance between them. So D. So it's 5 into 5, 25. Okay. I've just taken a random value there. I'll just try. Let's try to just do a quick question on this. So first force 5 Newton at a distance 3 centimeter or 3 meter from the pivot. Other force 5 Newton at a distance 4 meter from the pivot. What is the total turning effect due to the two force, or what is the turning effect of the moment here? of the couple here, not the moment.
7 into 5,
7 into 5,
which is 35.
which is 35 Newton meter. Clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. Whenever they say moment, no, whenever you need to calculate moment, it's compulsory that you write the direction. Okay, don't avoid it. Okay, let's do a similar question here. At a distance of 1 meter from the pivoted point, 7 Newton. Another force at a distance of 3 meter from the pivoted point. Can you calculate moment of couple in this case?
7 into 2,
7 into 2.
7 into 2 meter, 40 Newton meter. Okay, clockwise or anti-clockwise?
Anti-clock.
and
The anti-clockwise is more than the clockwise. Okay, so this is what the formula is trying to teach you. Can we not calculate the for this like the net moment of the couple without this formula? We can individually calculate this moment and that moment and add it, right? Okay, so it's not really necessary that we use the formula, but if you understand the formula, you can use it in these special cases where the two forces are opposite to each other but equal in magnitude. Am I clear? So this is a
Yes.
special case, it's not even a general case, can be used everywhere.
So
Yes,
the distance is different, they cancel each other, but what if the force is different?
then it's not a couple.
Oh,
Okay, that's a general case, so there you just individually calculate the moment and add it based on their signs, whether it's clockwise or anti-clockwise. Okay, so this is just a special case. Couple is just a special case where there are two opposite equal forces act on a body which is pivoted at a point, but in opposite, but not along the same line. Okay, if they act along the same line, they will then cancel out each other. Then there is no moment of the couple. Okay, moving further. Equilibrium of bodies. What do you understand by equilibrium of bodies? When do we say a body is in equilibrium? Whenever a number of force acting on a body produces no change in its state of rest or motion, the body is said to be in equilibrium. Okay, so there must be no change in its state of rest or motion. Then we say body is in equilibrium. Like like if an object is lying on a desk, is it in equilibrium? Because if we keep on observing the body, there is no change in its state of rest. It's just there. Okay, if a book is kept on a table, the book is there. The state is not changing. But are there any forces acting on that book?
yes, sir.
Certainly, there are forces acting on it. Okay, we know there is a force of gravity. Table is applying a reaction force on the body. So all these forces which is acting on the body are maybe cancelling out each other, and hence it is in equilibrium. So we have already have a understanding about equilibrium of forces from last year, that when net force is zero, there is no acceleration. That's what we studied in Newton's law, right? When there is no net force on a body, there is no okay. So when there is no net force on a body, then there is no translation. Means the body does not move, or it continues to move in its state in a state of uniform motion. That is also there. Either body won't move or it will continue to move in its state of uniform motion. Equilibrium are two kinds. It can be a static equilibrium or a dynamic equilibrium. Static means when the body is at rest, and dynamic is when it's moving. Clear? Like for example, if a book is kept on a table, okay, I think that's there in the next slide. So here, yeah. When a number of force acting on a body which is in the state of rest such that the body continues to be in the state of rest, it is said to be in static equilibrium, like the book on the table here. Okay, this book is under influence of several forces. The downward gravity force, which means the weight, and the upward cancel out each other, and therefore there is no resultant force on the body. And hence there is no translation, means the body doesn't go up or down. Clear? Second is dynamic equilibrium. When a number of force acting on a body, which is in the state of motion, such that the body continues to be in the state of rest. Oh, sorry. When a number of forces acting on a body, which is in the state of motion, such that the body continues to be in the state of motion, it is said to be in dynamic equilibrium. So if a lot of forces are acting on the body, but all these are like maybe all these forces cancels out in such a way that the body continues to move at the same speed, then it is in a dynamic equilibrium. So in this case, the speed does not change. The speed remains same for the dynamic equilibrium. Here we have an example of a car. See, in order to move this car at a constant speed, like you must have experienced sometime when the car is going at a constant speed of 100 kilometer per hour. Okay, so we have fixed the limit. The car is fixed at 100 kilometer per hour, so the speed can't increase. Now this car is moving at a constant speed of 100 kilometer per hour. Okay, so just if you have observed the situation, obviously I know you are not driving the car, but if you have curiously observed the driver, is the driver accelerating to maintain a speed of 100 kilometer per hour, or can he just remove his legs from the pedal, like from the accelerator, and still the car will continue to move at 100 kilometer per hour? In order to maintain speed of 100 kilometer per hour, does the driver still needs to apply accelerator? Anyone?
Once in a while.
Once in a while. Okay, anyone of you have tried a scooty?
Yeah.
You know how to drive a scooty? Okay. So
No.
when you drive a scooty and you leave your accelerator, the speed remains same or it reduces.
It's
Reduce.
reduced.
Okay. But ideally, when we apply accelerator, means we are applying a force. The speed must increase. Okay, that happens in the beginning. But after a point, like if your speed, let's say, if your the scooter limit is 70, 80 kilometer per hour. Now after that, even if you accelerate, the speed doesn't go high, but you still need to continue accelerating to manage that speed, right? So how is it possible that under influence of acceleration of force, the body speed is not increasing? See, it is certainly because there are more than one force which is acting on the vehicle at that point in time. So it's not the accelerated force only. There's always a opposite friction force which is acting on the scooter. And these accelerator force and friction force cancel out each other at maximum speed. Okay. So even if a body is moving, it's constantly moving, and the net force on body is zero, means you're applying two forces on the body, and these forces are opposite direction, and they are canceling out each other. So the resultant of this would mean that there is no net force on the body, and body will continue to move at the same speed. Clear? So that is the example of dynamic equilibrium. All this we have already done in force last year also, that if a body, there is no net force on the body, means all the forces cancel out each other, the body does not accelerate. Correct?
Is it uniform motion?
It is uniform motion. Yeah, the speed remains same.
Yeah.
Okay, so this is Newton's what do you call Newton's first law. We are just recapping kind of the same, right? If a body does not, if the net force on the body cancels out, or the net force on a body is zero, then body will either stay at rest, like that book on the table. Here all forces are canceling out and body is at rest, so it continues at rest. Or the second case, where the car is going with uniform acceleration, like is moving with a uniform speed. In this case also there are forces, like the acceleration force is there, and there is a friction force which is acting in the opposite direction. These forces are cancelling out each other, and that's why the car is moving at uniform speed. Correct. So the net force here is zero. So that way we can say the car is in dynamic equilibrium. Okay, so you understood the difference between static equilibrium and dynamic equilibrium? Static is when the body is at rest. Yeah, my bad. So static is when the body is at rest, and dynamic is when the body is moving at a uniform speed. Okay, see, all of this was even there last year. Then what is the point of learning this again? So that's when we come to the most important part. Condition of equilibrium is not just about having a like equilibrium in translation, but it also means having a equilibrium in rotation. There is a body like this. You remember in force we used to treat all like force or part motion last year. We used to treat every object like a point object. Correct. Now let's think the body. This is the object. It is fixed at this point, or this is the point of pivot. Let's apply two forces on this object. Or let's say it's not even fixed. There's an object like this. We are applying two force on the object, like this 5 Newton in this direction and another 5 Newton in this direction. Can you tell me what is net force on the object? Net force.
Zero.
Net force is zero. See, please try to understand. This is a very important point I'm trying to help you understand. So here in this case, net force is zero. If net force is zero, means there would be no translation. That means body is under translational equilibrium. Okay, that means if it is at rest, it will continue to be at rest. So assuming that this body is at rest right now, and it experiences these two forces all of a sudden, like two opposite force comes and starts up acting on this body from opposite direction. Since these two forces cancel out each other, body won't move forward. But now just imagine this situation in your real life. There is one object hanging like this. Okay. and you apply two forces on this object. Okay, this is a pen and you're holding it like this, and you apply two forces on it in opposite direction. What do you think? Will the object move? Do you think this object will move? Two opposite forces are acting on it.
Yes, sir.
In what way? Like, what's the nature of this motion? Is it going forward or is it just rotating?
It's rotating.
It is rotating. See, if you apply two opposite force on the pen, right, it rotates. It doesn't go forward. Okay, that means it has a translational equilibrium, but the body does not have a rotational equilibrium. Okay, body is translating, but it is not rotating. So it is rotating, but it is not translating. You understand my point? Okay. Just again a small question. Like, let's say with respect to this point here, like just I have assumed a fixed point A here. With respect to A, what is distance of this force? Let's say this distance is 2 meter, and this side is also 2 meter. Can you help me calculate the net turning effect, net torque due to the two forces? What is turning effect due to the top 5 Newton force?
10 and 10. So
10 Newton meter. And how much is turning effect due to the other
10
10 Newton meter again? And their sum is 20 Newton meter. Are they in same direction or opposite direction?
opposite. So they're a couple.
It's a couple. So their turning effect is same, right? Okay. So it is both are clockwise or anti-clockwise?
Clockwise.
Clockwise. So the total turning effect is 20 Newton meter clockwise. Correct? So in this case, you saw that there is no net force. Okay. That is why the body was not translating, means this pen was not going forward. Okay. But there is a net torque, and that's why it's rotating. You understood my point? Let me just repeat what I am trying to say. Since there is no net force, body is at rest, there is no change in its speed. Okay, it continues to be at rest. So it has a translational equilibrium. But since the torque is not zero, it does not have a rotational equilibrium. So in order to maintain a complete equilibrium, then not just the sum of force must be zero, but even the sum of torque must be zero. Okay. The other way of telling that is, if force is zero, if force is not zero, body will continue to move forward. Okay. If the algebraic sum of force must be zero, if the body is if the net force is zero, then the body is won't move. Like okay, but if the net force is not zero, body will translate, means it will go forward. Okay. While if the algebraic sum of moment, okay, if the algebraic sum of moment is not zero, then the body will rotate. Okay, let me take an example. Like
So
if a fan is moving with a uniform speed in circular direction, okay, it's a rotational motion. In this case, is fan moving forward or backward? So what do you think? What is net force on the fan? How much is net force on the fan?
0.
Zero.
Zero. But is torque zero? Net torque? Summation is
No.
for sum. Torque is not zero. Clear? Okay. Next example. This box, which is moving in a straight line with a uniform speed. Or if it is moving in a straight line with acceleration, let the speed increase. Okay. So it's going in a straight line with a changing speed. In that case, is force zero?
No.
No. Is it rotating about a point?
No.
No. So is torque zero?
Yes.
Yes. Okay. If the torque is not zero, then it will start rotating about the point. Okay. What about this wheel which is rotating? This is wheel of a cycle. Okay. The cycle is going forward with an increasing speed. Speed is increasing, and the wheel is also turning. In this case, is force zero? It's going with increasing speed, velocity. The wheel is going forward.
Force is not 0.
Force is not zero. What about torque?
No.
No, it's not zero. So what I'm trying to help you understand here is that if force is zero, then it will either stay at rest or it will like continue to move at uniform speed. Okay. But if torque is zero, then it won't rotate. So there are two types of motion. One is translational motion, Nature of translational motion is detected by the net force on it, while the nature of rotational motion is detected by the net torque on it. Am I clear? This is the principle of moment. It says, okay, this is also important. Remember this principle of moment. At equilibrium, sum of clockwise moment is equal to sum of anti-clockwise moment. Okay, so if when the body is at equilibrium, sum of clockwise moment is equals to sum of anti-clockwise moment. Okay, we'll just see one or two small numericals. In schools, they haven't started with numericals yet for all your sections, or in some of the sections they have.
We
Sir,
started.
they started.
They started. Okay. Uh, Actually, this chapter doesn't have much of theory. Sorry, theory. This is we mainly covered almost 90% of the theory here. There's hardly 10% more, but I think the questions are which sometimes creates a little trouble. But then it's all about practice. Okay, if you do the Selena question itself, is more than enough. These questions which I put in the slides are all from Selena. So first we'll try to cover all Selena books, and then we'll see some more from other places. ABC are three forces, each of magnitude 4 Newton, acting in a plane. Oh, sorry.
So I found
Yeah. It's here. ABC are three forces, each of magnitude 4 Newton, acting in a plane of paper. Okay, you can see the question clearly. No, the diagram I hope is fine. So, which force has least moment about O? Which of the three forces have least moment about O?
C.
C. Can you explain why?
No. A. Yeah, because more the distance, lesser the force.
Is it like that? First of all, we are not talking about force. We are talking about moment, the torque.
Oh,
Formula for torque is force into distance. So greater the force, greater the torque, greater the distance, greater the torque. So the two ways of increasing the torque, either by increasing the force or by increasing the distance. So which has least moment? Yeah, and which has least moment about O, A, B, or C?
So, C.
C has least moment. Reason?
So, because it has like the shortest distance
Okay.
between the
So
pivoted point and.
the perpendicular distance of of C force is least, or C has the least perpendicular distance from the pivoted point. Which force has greatest moment about O?
E.
A has greatest because this has maximum distance from the pivoted point. Name the forces producing A clockwise and B anti-clockwise. So which all are clockwise and which all are anti-clockwise? A, for
E.
example.
A
A
A
is
is
clockwise.
clockwise and B is,
Clockwise. C is
and C.
anti-clockwise.
Okay, this and all you understand. Very good. What is the resultant torque about O? Okay, so we need to find the net torque. Okay, let's do torque A plus torque B plus torque C. Torque A is 4 into 0. Okay, 4 into 0.8 and 4 into 0.6. Also, we must write clockwise, clockwise, and anti-clockwise so that we don't get confused. So this is 3.6 plus 3.2 plus 2.4. So the resultant is 3.6 plus 3.2 is 6.8. 6.8 minus 2.4 is how much?
So, we should minus it, right?
We are subtracting. That's why like either you minus it or you just write clockwise, and we are using, so 6.8 and then 2.4 we minus because it is anti-clockwise. So that is 4.4. Okay, and the net direction is clockwise.
Clockwise.
Okay, even suppose if you assume like clockwise is positive, anti-clockwise is negative, and then finally in the final step you get 4.4 positive and say it's clockwise, that's also okay. That's allowed. Means it's not wrong to do like that. Means wherever it is clockwise, you can take that as positive. Wherever it is anti-clockwise, you can take that as negative, or vice versa. And then just find the final answer, and then just at the end must just mention what is the net direction. Is it clockwise or anti-clockwise? So please do mention that also. Simple. Okay. So we'll just see one more question. This is the first from the exercise. Easy. Moment of force of 20 Newton about a fixed point O is 10 Newton meter. Calculate the distance of point O from the line of action of force. Force is 10 Newton meter and force is 20 Newton. Calculate distance of point O from the line of action of forces. So D is what we need to find. Moment of force is nothing but torque, so we'll just write tau. So how much is D then?
Torque upon force.
Sorry, torque upon force.
2 meters.
1 by 2 meter, which is 0.5 meter. 1 over 2. We divide torque by force, not force by torque. Because torque is force into distance. That's the original formula. Torque is force into D. So D is torque upon force.
Yes, okay. Yeah.
So we'll do one last question. This is also simple, so we'll finish it off. A nut is opened by a wrench of length 25 centimeter. If the least force required is 10 Newton, find the moment of force needed to turn the nut.
Torque divided. we-
So what we need to find torque.
Yeah.
Just force, right?
Yeah, least force is, see, because we are holding the wrench at the maximum distance.
Oh,
Okay, you can't hold farther than that, right? So since you're holding at maximum distance, you will be applying the least force, because when the so torque is equals to force multiplied with distance. Here the information given is force is 10 Newton and distance is 25 centimeter. Okay, we convert that to meter. That's compulsory. That is basic in physics. We always convert it to the required unit. If everything is in SI unit, we convert it to SI unit. So 1 by 4 meter. So 10 Newton multiplied with 1 by 4 meter, that is 2.5 Newton meter. Clear?
yes, sir.
Okay. So I hope you all of you understood this. Okay. I'll share this PDF immediately so that you can use it for revising even for your test tomorrow. Okay. Till here, I'll share it right away. Okay. I think that's then fine for today. See you again in next class. Thank you and bye for now.
Fine, thank you,
Fine.
sir.
Fine, thank you.